So today we are going to be looking at sampling distributions for the differences of means and proportions. So specifically a two-sample sampling distribution for means and proportions. And follow us on all your social media platforms, including TikTok, which I've had some fun with over the past week, and Twitter, Instagram, and YouTube at ThinkFiveable. Okay. In this stream, we're going to look at the definition of a sampling distribution, what a sampling distribution is going to be like for two proportions, a sampling distribution for two means, and then also look at a COVID-style free response question for this year's upcoming AP Stats exam, because we do have a lot of kind of unanswered questions with the new exam format. So I'm going to try my best to give you what seems to be the idea of what a free response question is going to look like for this year's exam. Okay. All right. So a sampling distribution, basically what that is it's a distribution that's going to use the average from all possible samples from a given sample size as its data set. Okay. So I'm thinking about taking all possible samples. I have a population and I'm taking all possible samples of maybe say 45. So if I take every possible sample of 45 and average all those values together, and then that becomes my data set that makes my distribution. Okay, so this one, in the example here is actually 30. Okay, so in a sampling distribution of sample size 30 of, say, math grades, we would take all possible samples of 30. So that would be, the sample with 30 people, and then the next one might swap out just two people. Two people change. One person's not in the sample and somebody else is. Okay, so every possible sample of size 30. That's a ton of different options, depending on, how big your population is. And then if you take the average within each sample, all of those averages becomes my data set that makes my new distribution, which is my sampling distribution. Okay. And like we said before, it is the crux of statistical inference. Without sampling distributions, we don't have statistical inference. We would not be able to calculate a p-value, a z-score, or a t-score, because all of those are based off of sampling distributions. Okay, so in terms of statistical inference, our p-value is the probability of getting that actual sample. So, for instance, we have a statistical claim from a hypothesis that says that the mean math grade is an 85. All right, well, then we take a sample of 30 and we get that the average grade from that set of 30 is a 72. Well, that's a pretty big difference between the 85 that the claim was and the 72 that we actually have. So the p-value is what is the probability of getting that sample size 30 that would give us an average of 72. Okay, if the true average of the whole population is an 85. And that's probably going to lead us to have a really low p-value, which, as you recall from statistical inference, means that we would reject that null hypothesis that says that it's 85. Okay, because there's such a rare chance of it happening that it probably didn't happen. Okay, winning the lottery is really rare. So there's probably something that made it, not random or something like that. Okay, and in this case, we're saying that their claim was actually false. Okay, so sample size is also really important. So when we're comparing sampling distributions, the larger our sample size, the more our data is going to pull in towards the true center. Okay, so it's going to pull in towards what that population proportion or mean is. So if we have a small sample size, we have a normal curve. I'm trying to put together my hands. Okay, something like this. And then as we make that sample size smaller, it's going to pull our data, our bell-shaped curve in closer and closer to hone in on that actual population proportion or mean. So if we have a sampling distribution with a larger sample, then that means that our population proportion is going to be better estimated because our samples are a lot closer to that population. Okay, so here's a little activity that I kind of put together with a really neat website, which if you want to see, I will put it in the resources tab on the replay. So you can go back and go to this website and play around with this. So this was my parent population. Okay. So somebody tell me in the chat if this looks like a normal curve or a symmetric curve in any way. Normal, symmetric, yay or nay? No, not at all, right? This is one goofy looking curve. I don't even know if I'd call it a curve, right? It's like tons of bumps and lumps. It looks like a city skyline, right? Okay, so this was my population distribution. And these are my two sampling distributions. So if I take a sampling distribution of n equals 2. So from this population, I took every possible sample of size 2 and averaged those two to create these data points. Would you say that this looks like it's symmetric or normal? Yes, right? Okay. Our sampling distribution of something that's completely not normal at all becomes a lot more normal when you take a sampling distribution of that data. And then as our sample size gets larger, yes, it is much easier on the eyes, Olivia, right? It looks more neat, nice and neat, not all over the place. Looks like something you can do some calculations with. And then when we look at our distribution with a sample size of 25, so I take all possible samples of 25, and then I take an average of those 25. That becomes one data point for this sampling distribution. Then I take the next possible sample of 25, average all those. That becomes my second sampling distribution. Okay, and then you keep doing that, and our second sample for my sampling distribution. And then you just kind of keep putting all those together. Then you can see it becomes even more normal, and it's honing in right there on that middle. So the true center of my population is right here. You can see it. All right, you can see it's the middle. And then right here, you can see that it's like the mode as well. Okay. And if I did a sample size 100, it would have been even more so sucked into that value there. Okay. So Taylor's stream is not working. I'm not sure what to say there. Use the link up in the top that says help and see if that will work. Can't see anything, but I can hear you. Huh. That is strange. Use the help link up in the top right above the chat where it says share, edit, and options. Go to help and see if you can figure it out from there, Taylor. That probably would be your best bet on getting that. If everyone else is hearing it or hearing and seeing, then it's maybe something with your browser not allowing video embedded. You might have to change an option like on your Chrome tab where it's not blocking a certain plugin or something like that from Crowdcast. That would be my guess, but you can use the help function there, and they probably can point you to what you need to do a little bit more than I can. Sorry about that. Okay, so yeah. Completely not normal population, not symmetric. Well, sort of symmetric, but definitely not normal. And then a sampling distribution, the sample size increases, it becomes more and more normal. Okay, so the big thing about a sampling distribution, okay, it's working now. Yes, woohoo! Glad you're able to get that figured out. Technology is just getting the best of us on this Monday afternoon, right? We're all on the struggle bus a little bit, but it's okay. We're going to work through. Okay. I'm just glad everybody stuck it out with me for the first few minutes, and we're all pushing along now. So, conditions for sampling distributions with two proportions. So again, as we kind of move into inference, so sampling distributions are the first piece of that inference piece. We kind of build that content, and then we talk about how we can use sampling distributions to make statistical inference. Okay. And so with that, in order to use a sampling distribution to calculate things that are really interesting, we need certain conditions. Okay. All right. So the first one, and this one, a lot of textbooks don't have this listed as being necessary, but I go ahead and throw it in because it works right in with the next units as you move into inference. Were our samples chosen randomly? Okay, we can't use our sampling distribution if the one sample that we have is not random. Okay, it's completely pointless to us to take a sample of all the people we wanted to ask a question and then compare it to what the population would be. Okay, we don't have a very good population if we didn't, take a random sample, if we just ask the people we wanted to ask. So our sample needs to be random. Okay. Independent. So when we're sampling without replacement, if you're sampling with replacement, then independence is kind of understood. But when it's without replacement, is it reasonable to believe that our populations are at least 10 times our sample sizes? Okay. So if we have a sample size of 30, is it reasonable to believe that our population is at least 300? If it is, then we can assume that even though we were sampling without replacement, the impact that our sampling had on each other by the fact that I removed person A and now I have one less person to choose from, that probability of selecting person B is a little bit lower or a little bit higher, I guess, because you did remove one person from the population. But if it's at least 10 times larger, we can say that that difference is so negligible that it's essentially independent. That's where that 10% condition comes in. And then the third one for proportions is we want to see if our sampling distribution would in fact be normal. Okay. And when you're doing proportions, this is something you're probably going to want to put on a little cheat sheet for this year's exam, is the large counts condition. Okay. So N1 times P1 times the probability among that first sample is greater than or equal to 10. N1, 1 minus P1 is greater than or equal to 10. And then the same thing for your second sample. Okay, so we're mainly focusing right now on two samples, which ultimately leads you to believe is the proportion from population A different than the proportion from population B. That's what you're ultimately checking. Okay. And that is our gist, what we're ultimately getting to with the sampling distributions of two proportions. Okay, so I have to check that with both samples. I have to look and make sure that my expected values, expected successes, and expected failures from both populations are at least 10. All right. Once we have checked those conditions, then we can construct our sampling distribution to calculate said p-values, if that's what we're doing, or whatever else we're looking at. Okay, and those are our two formulas. Okay, we have to calculate a mean, which is just you're subtracting your two population proportions. And then you have to put together your standard deviation. And then once you have a mean, a standard deviation, and you know you're dealing with a normal distribution, voila, normal CDF is now your friend. Okay, if you're using a calculator. If not, calculating a z-score and doing your z-score table to calculate your probability is now your friend. Okay, I would recommend technology and using normal CDF. It's a lot easier. But yeah, like thinking back to what you would put in your calculator, your normal CDF, you have your lower upper limit, and then you have your mean and standard deviation. So these are the two things that you need to find. Okay, so kind of a messy formula. However, those are on your formula sheet. So we will talk about those more in a few weeks when we have that stream coming up. Okay. So an example, it says a recent survey is administered to both ages 21 through 29 and 31 through 39 about whether or not they believe that the earth is flat. A simple random sample of 100 adults aged 21 through 29 and 100 adults aged 31 through 39 are polled. The 21 to 29 group comes in and saying that 12% said that the earth is flat. And the 31 through 39 age group comes in saying that 10% of them say the earth is flat. So here are our two populations, our two samples. So A, it says check that the conditions for constructing a sampling distribution are there. So check those conditions. What is the first condition we have to check? Type that in the chat. And then random. Do we have random though? Does it say that in the problem? Yes, SRS, which simple random sample. Okay, so a little word of advice for this year's AP Stats exam. You're not going to be doing like a written test. In the past, a lot of teachers have just said to like circle that on the test booklet. because then they'll give you credit. Well, now that you're doing it on your own paper and uploading it or even typing it up possibly, I would quote like a simple random sample of 100 adults aged 21 to 29 and 100 adults, ... So make sure you quote the problem that includes the simple random sample of however many. Okay. So just make sure you get credit on that, because that is like an easy thing that you have to check. And it's very important, because if it's not a random sample, well, then you can't generalize it to any type of population. And that's what we're after with inference. Okay. Which starts with sampling distribution. So yes, both samples are random, an SRS of 100 adults. So you can see how I kind of quoted that. You know, the reader can know that I know that it's random. And we just want to make sure we convey that to the reader as good as we can. Don't miss points on forgetting to say that a sample is random with conditions if that happens to come up. That would just be a shame. All right. Oh, I forgot to ask about the next one. Independent. Yes, it is reasonable to believe that there is more than 1,000 adults in both age groups. Okay, that's definitely reasonable to believe, right? We're talking about all adults. It didn't even say U.S. where they polled them. It could be all around the earth that may or may not be flat. All right, so what is the third condition? Normal, exactly. If we're doing a sampling distribution, to have anything special about that sampling distribution, it needs to be normal. Okay, and you can see I checked those. All of them are greater than or equal to 10. Okay, 12% of 100 is 12. 10 is equal to 10, which is fine. Greater than or equal to. And then 0.9 is greater than 10. Okay, that's a really great question, Nell. You cannot use n greater than 30. N greater than 30 is the central limit theorem, which only applies to means. Almost said memes there. It only applies to means. So since this is a problem where we're dealing with proportions and we're ultimately going to proceed with a z-test or a z procedure, we cannot use n greater than 30. Okay, that will come up on part 2 in just a second. So that's a really important thing that this year y'all have a little bit of an advantage to, because you can write those two things on your formula sheet, your cheat sheet, whatever it is you're making. You can write proportions, large counts condition, NP greater than 10 and 1 minus P greater than 10. Means, central limit theorem, N greater than 30. Okay. You can write it on your formula sheet. You can print that out, write it on your formula sheet right beside the formulas that go for those. Okay. It's one of the things we'll talk about in a few weeks. So anyways, very definitely important there to differentiate between that. One of the most common mistakes people make. And this year, y'all have the open notes option of having that there with you to not make that mistake. Okay. So conditions are there. We do have a normal sampling distribution. Okay, same problem. Find the mean and the standard deviation of the sampling distribution for the difference in the population proportion. Somebody over there in the chat, tell me what the mean of the sampling distribution is going to be. I'm not going to make you do standard deviation, but the mean should be pretty easy. You can do it in your head. So what is the mean of the sampling distribution here? All right, now can you be a bit more specific in how to write it instead of saying 2%? Okay. Yes, I like the way that Allie wrote it out there a little bit better. Written as a proportion, as a decimal instead of a percent. College Board can be kind of tricky with percents sometimes. I would stick to writing everything as a proportion. Now, when you do probabilities, you can do percents, and I've seen that accepted before, but I've never seen them not accept a proportion with the decimal form. So 0.02 would be the better way, because think this is going in the center of your normal curve. That's going to be your mean. So that's the center of your normal curve. Thinking about it as a decimal for the x-axis as opposed to a percent just makes a little more sense, because we are going to have some that are negative. There is a chance that a sample from the 31 to 39 age group is actually higher than a sample from 21 to 29. So that is possible. Okay. So that is the mean, 0.02. So even though it's worded as percentages here, we want to take that percentage and redo it to a proportion before we subtract them. I just think that looks a little bit better than the 2% there. Okay, and then standard deviation is the other one. I put it into my calculator and took a screenshot because that looked a lot easier to me. Okay, so I have my P1 times my P2, or 1 minus P1, all divided by my N1, 0.12 times 0.88 divided by 100, plus 0.1 times 0.9 divided by 100, and that comes out to 0.044. Okay, so that would be your standard deviation using the formula that you have there. Okay. I would recommend using a calculator to do that. I highly doubt this year they're going to ask you to calculate those with having a calculator to use. And this is a pretty long calculation. Even if it's just a four of those, I would make sure you have those. All right. So that's our mean, and that's our standard deviation. So you can think, normal curve, empirical rule, adding so many standard deviations and subtracting so many standard deviations to sort of put together our curve here. Okay. Oh, man, my answer already came up. Oh, well, we'll talk about it. In our sample, we get a difference of 5% in the two proportions. Find the probability of achieving at least a 5% difference in the two proportions. Okay, so as you see, I went ahead and went straight to my normal CDF. My lower limit was 0.05, 1, because I can't have a proportion that's more than 1 anyways. Okay, and it's more than 3 standard deviations away from that number. Okay. My mean was 0.02 from my previous slide. My standard deviation was 0.044, which gave me a probability of 0.247. So basically, I take a sample, a small sample, and I get that the difference is 5%. Okay, so instead of 2% difference, it's actually 5% difference. And that makes me think, oh, well, are they wrong by saying 2% different in the, the article that we have? Okay, because my sample is 5%, and that's a good bit higher. All right, well, using the statistics there, I can see that it's probably just due to sampling variability. Okay, the probability of getting my particular sample, if they were right, is still about 25%, which isn't that rare. There's no wow factor to that probability. If there's a 1 in 4 chance of me winning the lottery and I win, I'm not going to be extremely shocked. I'll be extremely happy because I won some money or something, right? But I'm not going to be extremely shocked, right? Because there's a 1/4 chance of it happening. But if there's a 1 in 100 chance of it happening and it occurs, then I'm probably more shocked. So this is where those p-values come into play. We just calculated a p-value. Our sample was 5%. From this p-value, would I reject the hoe or would I fail to reject the hoe? What do y'all think? Reject, fail to reject. Nell says fail to reject. Anybody agree, disagree? Not sure. Fail to reject. Fail to reject. I agree. Good. I think we're on the same page. Yes, we would fail to reject because it's not that low. Okay, there's no wow factor. Rejecting the hoe always comes when there's that wow factor, that really big, that really low probability that we're like, oh, wow, like that shouldn't have happened, but yet it did. And that makes me think that something is off with what they originally claimed. Okay, because we know our sample's random, so it wasn't because we took a biased sample. And the chance of it randomly just occurring is not that rare, so it's probably another issue there. Okay, and it's probably that they were lying in the first place, or maybe this was biased. Okay, all right, I think that D is. I might have got a little bit ahead of myself. Oh, no. Whoop. Let's go back. I want to go back. All right. So let's change gears now and look at when we're looking at two means. So we have to check our conditions. Okay, so same thing. So now we're, instead of looking at two proportions, we had those formulas. We looked at how to calculate a probability for that. What happens when we have two means? Okay, we have the same conditions. Okay, pretty much copy and paste, right? So random, were our samples chosen randomly? If they're chosen biased, then it does us no good. We can't make any inference to a population. If I only ask my friends a question, well, then I could make an inference to all of my friends, but that's not really helping me much. I want to make an inference to, say, all teenagers, okay? So I need to take a random sample of teenagers, not just my friends, okay? Whatever you want to make an inference or make a to make a judgment about big picture, that's what you need to randomly choose your sample from. Okay, going back to like Unit 4, that the non-math chapter. All right, so 2, independent, same thing. When we're sampling without replacement, we have to make sure that it's reasonable that our populations are at least 10 times our sample sizes. Okay, if it's not 10 times our sample sizes, then the without replacement is probably affecting things. Okay, but usually that's pretty easy to believe. Okay, if I'm talking about all adults, it's usually reasonable to take our sample and multiply by 10 and say, yeah, we good. All right, and then 3, this is where the central limit theorem comes in that came up earlier. All right, I got to make sure that both of my samples, since I have 2 means, I have two populations I'm comparing, I have to make sure that both of them are at least 30. Okay. Or second thing, if our samples are small, well, maybe, they're small and we're like, we don't have central limit theorem. What can we do now? If it's given in the problem that our population is normally distributed, then our sampling distribution is also normally distributed. So going back to that example I gave earlier where I had that really weird curve with all the humps in it, if that would have been in a normal curve, well, both of my sampling distributions would have been even more so normal. Okay, so if our populations are approximately normal, our sampling distributions for that size are also approximately normal. Okay, or this is kind of a last-ditch effort. If it doesn't say anything in the problem about the population being normally distributed, we can draw a box plot of both sample 1 and sample 2 and show that they are not strongly skewed. They can be a little bit skewed, but not like outrageously skewed, and also show that they do not have outliers. If it's a somewhat symmetric box plot for both samples, then we can assume that it's approximately normal. Okay, that has came up in AP questions before, but the first 2 should be your first option. They're a lot easier to prove. Okay, they're a lot easier to show. That's a good question, Allie. I really don't know if they're going to make you do a box plot online or not. I want to say no. I want to say they're going to give you the box plot and make you jump and make the inference. Like they might give you a box plot and then swap gears and make you say that it's approximately normal because both box plots are not strongly skewed or have outliers in the next part of the question. But I don't think they're going to make you draw one. Again, that technology inequity piece kind of comes in there. Yeah, it's a good way to draw one. I like that. Just make sure you end your whiskers and don't put another dot outside of it because that would be an outlier. But creativity, I guess, right? So again, once we've checked our conditions, we can construct our sampling distribution with the formulas. The formulas for 2 means are a little bit different. They're actually a lot easier to calculate. So for the mean of your sampling distribution, you're going to subtract your 2 population means, which should be given in the problem. For your standard deviation, you're going to square your standard deviation of your population, divide it by the sample size, add it with the same thing of the other, and then take the square root. Okay. So that is how you get your mean. You have your standard deviation. From the previous slide, you've checked that it's normal and random, of course, and independent. So therefore, you have everything you need for a sampling distribution to calculate p-values, okay, which is exactly what we're doing. Now, on the last one, if we were using it on a calculator, we would have used the normal CDF. If we're dealing with 2 means on our calculator, what calculator function, how would that be a little bit differently with means? Instead of normal CDF, which one would we use instead? Y'all throw that in the chat. Not z-scores. Z-scores is normal CDF and proportions. There's a little bit of a hint. So that normal CDF. Oh, you're close, Allie. Not inverse T, but you're on the right track. Okay, 2 prop t-test, yes. Nope, not inverse norm. It wasn't the normal part. It's the T part that we're looking for. Not necessarily. Well, a t-test is going to do this for you, but the t-test is doing that. Okay, it's doing the t-CDF. Okay, that p-value within a 2 prop or a 2 sample t-test. So let's, Allie, whenever you said 2 prop t-test, this wouldn't be proportions. This would be means. So it would be a 2 sample t-test. Okay, you're good. Okay. I just wanted to clarify that because I didn't catch it the first time. So yeah, a 2 sample t-test is going to calculate a p-value by doing that t-CDF. We don't use t-CDF a whole lot because by the time we've gotten to the t-curve, we're just doing the inference. Okay. We're just doing the t-test and letting it do its thing. But a t-CDF works the same way as normal CDF in terms of calculating that probability of getting that sample, but it does it based off of the t-curve, which is slightly different than the normal curve. Now, if you have a t-curve with infinite degrees of freedom, then you will have a z-curve. But, you know, and that comes down to the fact if you know the population standard deviation, then you can use a z-score and a z-test. But that's really rare, and you don't really see that very often. Okay, so anyways, so kind of to wrap things up here, we're going to look at another example, and this is for a sampling distribution for the difference of 2 means. And we'll kind of look at multiple parts and kind of branch out to some other units and some other topics using what we talked about today. All right, so it says we take a sample of 5 large French fries from Burger King and find that it has an average of 45 fries with a standard deviation of 2.3 fries. At McDonald's, our random sample of 5 large fries had an average of 75 fries with a standard deviation of 8.1. Both restaurants' distributions are approximately normally distributed. So all fries from Burger King, normally distributed, and all fries from McDonald's are normally distributed. Okay. So A, what type of study is this? Explain why this is important. So we have 2 types of studies we generally talk about. Not what type of test we're doing, but what type of study is this? Observational. Yes. Yes. Getting a lot of those. We have observational and experimental. Okay. If you've been following along with me on Five over the past few weeks, you probably know that I'm going to throw that in there on every question because it's like the golden rule of stats, one of the golden rules. And I don't think it's a test. Okay. So what makes it observational? So what about it? How do we know that it's observational? Okay, Josie, Allie, yeah. I would say no treatments assigned because, I mean, there's not really given either. But, yeah, I would say no treatments assigned. Okay, and since there's no treatments assigned, why is this important to the question? Yes, Kate. Yes, Allie. So we cannot show causation. It may be correlated, the restaurant and the size of fries, but we cannot say that it causes the fries. Okay. Observational, we're not assigning treatments. We are simply observing the number of fries at each restaurant. We're not assigning Burger King to do something, McDonald's to do something. This is important because it means that we cannot establish a cause and effect restaurant and number of fries, but only a correlation. All right. I'm not saying Burger King, you pack this amount of fries, and McDonald's, you pack this. Then I could do whatever I want, I guess, and say that, yeah, Burger King caused a smaller number of fries because I'm set it up that way, I guess. So yes, observational, no treatments assigned. That means that I cannot establish causation or a cause and effect, but only a correlation. Good job. Make sure you have that nugget of information ready to go on May 22nd. I really think it's going to show up somewhere. Okay. All right. Same question. Part B, a sample size of 5 is pretty small. I mean, I could go for some large fries right now. I'm kind of hungry, you know. I don't know if I just want. Actually, 5 large fries would be quite a bit. So, but it's a small sample. Clarify why that sample size is not necessarily important to have a larger sample size in order to continue making inference judgments. So what about this problem means that the small sample size is kind of not important? Each fry has many fries. No, it doesn't have to do with how many fries are in, because we don't take the average. We don't say that 45, okay, we don't say that that's greater than 30. Nope, not observational. Not enough data, nope. Think about what we do after. Okay, Olivia is on the right track. Okay, since both restaurants' distributions, the population of all fries at Burger King and all fries at McDonald's, not just my sample of 5, but it tells us that all of them are. Well, that means my sampling distribution of size 5 is also going to be normal. Okay, since it is given that both of our populations are normally distributed, we need not meet the central limit theorem of at least 30. Since our populations are normally distributed, our sampling distribution for the difference of the two populations will also be approximately normal. Okay. So yeah, our population is normal. That's really the best. You know, we have 2 bell curves, McDonald's, Burger King, and we're putting those 2 bell curves together. Well, that's going to make a bell curve type shape. Okay. And that's kind of what we have here. Okay. So that was kind of the second way of checking normal with sampling distributions with 2 means. Central limit theorem is our first go-to because it's really easy. Then we can look and see if maybe it says in the population if it's approximately normally. If not, we need to draw out a box plot of our sample, which here we couldn't do because we don't know the 5 large fries that gave us that average and standard deviation from each restaurant. All right, calculate the mean and the standard deviation. So y'all tell me what the mean is in the chat. Standard deviation. We'll do with a calculator because it's kind of nasty. But mean, y'all should be able to do. What would be the mean of our sampling distribution for the difference in the 2? What do y'all think? What is our mean going to be? It's 30. Because we take 75. I just took the largest one. It really doesn't matter because if you have it in the positives, the middle's at 30. And if you shift it to the negatives, it's just negative 30. It's really the same difference. Okay, so the mean is 30. So the average difference between the 2 samples is 30. And our standard deviation, nice little formula there. Again, I use my calculator. Okay, let's see. So D, it says we found that the standard deviation was 3.7656. Interpret this value. So kind of throwing things for a little bit of a loop because we have standard deviation. We haven't been asked to interpret that in a little while, okay? We're focused on inference here and that sort of thing. And now we are interpreting standard deviation, okay? So good chance to review that definition back from like unit 1. On average, a sample of 5 Burger King and 5 McDonald's large fries will have a difference of about 3.7656 fries from the average difference of 30 fries. Okay, so the average difference is 30, but on average, there's going to be difference by about that much. So our standard deviation is how far you are from the middle. And we identified our middle as the difference being 30. So on average, a random sample of 5 from each is going to be different by about 3.7656. Okay. Standard deviation is how different is it on average. And in this case, we're talking about how different is it on average from the 30 that was the middle. On average, it's 30, but there is a difference of about 3.7656 fries from that 30. Okay. So that one's kind of tricky. I was trying to think of something different to bring in. Like this is a definition from chapter 1 from unit 1. Okay. Probably been a while since we talked about standard deviation and what that means. So bringing that in, I thought was important to kind of review. I could see that being an interpretation that pops up. They might give you the answer and then ask you to interpret. You know, okay. Does that make sense? Any questions on that one? Feel free to pop questions in the ask a question tab or the chat. Okay. All right. And I think this is the last part. It says we take another sample and we find that it had an average of 35 fries. Okay. Is this enough evidence to doubt our other findings? And this one's kind of, it ties in with the previous question. Okay. So remember, our standard deviation was 3.76. So a difference of 35 fries is less than 2 standard deviation away from 30. Okay. 2 standard deviations would be 3.76 times 2. 6, 7.5. So 37.5 fries would be quite a bit different. Okay. That would be 2 standard deviations away from the average, which if you think back to the empirical rule, 95% of your data is within 2 standard deviations. Okay. So anything outside of 2 standard deviations is, less than 5% chance, which is kind of what we compare to. But in this case, it would not be enough evidence to reject our hypothesis that the true population means have a difference of 30. Okay. Could have done a little test there to determine it. But really we don't need to, because we can just see that our sample of 35 is within 2 standard deviations of that 30. Therefore, it's really not that odd. Okay. Kind of looking at making inference judgments from something other than a p-value. We can also make it from our, standard deviations, z-scores, and t-scores. Okay. All right. So I actually also did a normal CDF. I should have done TCDF there. Whoops. It would have been pretty similar, and 10% not that off. Okay. All right. Any comments or questions before I hop off of here? Okay. Any questions? Glad to go back to another slide. I know it's been a crazy technology. I'm seeing on my Slack channel that other Fiveable streamers are having the same problems that we had tonight with Crowdcast giving issues tonight. So anybody have any questions on sampling distributions or anything regarding what we talked about tonight? All right. I'm not seeing anything. Hopefully it didn't crash with you guys and I didn't lose you. But I hope that you all are doing well, continuing to prepare for your AP. Oh, man. And now I'm getting answers from like a long time ago. Okay. All right. Olivia says she's good. Allie's good. I'll hang out for another few minutes. I think it's kind of catching up with a lot of people. We're on a little bit of delay, maybe. So yeah, sampling distributions. I think sampling distributions make more sense after you do inference, after you do confidence intervals and significance tests. Then all of a sudden, the sampling distributions make sense to you. The first time I learned sampling distributions, I was like, okay, it's just another thing. I just got to change my standard deviation and then calculate my probability the same way. But then when you do inference and you see the value of that p-value, then it really makes sense. So anyways, I hope that you're all good. I hope that made sense. Be sure if you need to go back and catch the replay. And that will help. Also hop over on the cram pass in a little while. And I hope you all enjoy that. See you next time.